let's look at, I can draw a line like this, right? What is the slope of this line? Slope of this line. See, you just look at the height, right? What is the height? This height is f of x minus f of a, right? So this is the height. What is the width? X minus a. If I take the ratio, I'll get the slope, right? Okay. So let me write that f of x minus f of a divided by x minus a is the slope. But now intuitively you can see that I can match this slope by drawing a tangent somewhere here, right? Do you agree? There is a tangent. So what is this point? This point is some a star, right? A star is between a and b. That means it's in the domain of the function. So if you look at the gradient at that point, that is f dash of a star, then I can write this as f of x minus f of a divided by x minus a, right? So I can write by cross multiplying, I can write f of x as f of a plus x minus a into f dash of a star, right? I can extend that to get this, okay? So you can extend beyond this also, but this is how you get your remainder form. By the way, you should note that this is exact equality. It's not less than or equal to, greater than or equal to, or approximately equal to. It's exact equal to. Okay. So now how do you extend this to, let's say, higher dimension? Can somebody tell me what is f of x? Well, this is true under certain conditions. It's not true for every function. It should be twice function. I can write this. So now what is the remainder form? Let's say f of x for every x in Rn. Well, I should always refer to the domain of f, but let's assume that the domain itself is Rn. Then f of x is, of course, I can, let me consider a point y instead of a. Okay, so f of y plus x minus y. Remember, this is a vector now. It's not a scalar. I have to take the transpose. All the vectors, I'm going to write it as column vectors, right? So I take the transpose, it becomes rho, multiplied by the gradient of the function evaluated at y. Okay, I'm going to take the gradient and evaluate the gradient at y. So that's what we get. Plus, this will be x minus y transpose multiplied by the Hessian multiplied by x minus y. So you'll get a number, right? X minus y transpose is a row vector. H is a matrix. So it's 1 by n times n by n. So it will be 1 by n, right? You get one row and n columns. So you'll get another row vector. When you multiply by x minus y, which is a column vector, right? So row vector times column vector, you'll get a number, right? Of course, there is a by 2. Well, what is the issue here? I'll write it as H star, okay, where H star is the Hessian. So let me go back here. So this is f dash of a star. A star is some, so I'm going to take the second derivative, evaluate it at a star. What is a star? Nobody knows. I mean, it's some point in the domain of the function. So similarly here, a star is the Hessian evaluated at some, let me call this as x star, okay, belonging to domain of f. Is that fine? So you guys remember this, right? You agree? Is that okay? Fine. Okay, let's look at a few things, okay? So some few observations which will be useful when we look at the algorithm and its analysis, right? Even a simple algorithm like gradient descent, right? So how do you analyze gradient descent?